Hello, good morning everyone. Today, inshallah, we will continue our lectures. I've dedicated this lecture upon your requests for an overview and revision on the previous topics. I will go for just an overview about our course from the beginning, as we will have our first midterm, inshallah, next Sunday. I hope the best of all of you, and I wish you a very good luck in this period. Please try to manage your time very good. Try to organize your time, put a good studying schedule in order to review all the previous topics and also with the rest of the new topics that we will go through. Of course, all of our course notes references, you will find them on Moodle, and also all the lectures are recorded on the YouTube, so you should be in a very good shape. Okay, I want to review with you once more the evaluation rules. First, the first midterm is going to be, or the first test is going to be 50%, and it's going to be within next Sunday, inshallah. And for the second test, it's going to be also for 50%. You should have, for the average of these two terms, T1 plus T2 over 2, rounded to 10. If you get 10, you are passed this course. If not, you will have to enter a second season evaluation exam, which is going to be 1 out of 100%, and it will be quoted to 20, and the student approved for the final grade, rounded to 10. Also, there is a special season with, with a global exam of 100%, and this is for the special cases according to the regulations of the university. That's also, all I want you to do is just to focus, and you have a very good chance even to improve your grades even in the first midterm, within the second midterm upon your requests. So all you have to do is studying very well and be prepared, and the exam will be very good, inshallah. Okay, I want you to review the previous work. I want you to remember going through matrices, definitions, types, everything, properties and operations, including addition, multiplication by scalar, multiplication of matrices, the equality, the inversion, the transposition, and focus, please, the propositions. Usually, most of the small questions or the questions that will ask you to do some extra effort, it will be related to the propositions. So you need to go through them very well. Number one, properties, operations, inversion, and especially the propositions. Go through methods for solving a system of equations. And this part is really very important part in our course, in application or in general about everything. So really, it should be, you should focus on this part, solving a system of equations. At least you should go through a unique solution, no infinite number of solutions, and no solution case. And the conditions behind each one of these cases. Also, the classic problem of linear algebra of having some constants, and you want to find the value of these constants in order to classify a system of equations, also looks really very tempting. And we saw this in the previous exam, so it's really very important just to go through them one by one and to try at least solve 2 or 3 of them. You have plenty of these problems in the worksheet. Okay, determinants and their properties, and this is really very important, just to remark the difference in propositions of determinants and matrices. And the set of row operations that's different between the determinants and the matrices. There will be just a small question about vector spaces and subvector spaces, and we already did go through this more than once, and I've reviewed and make just a recap in the previous lecture about the basis or about the beginning of the issue of vectors and subvector spaces. Number 5, go through the solution of the previous midterms and the final exams, all recorded and solved with you. I've already did that previously. I believe you will find them in week number 6. In specific, I've sent these PDFs, and also you will have the recorded lectures on my YouTube channel. So you should be fine. I want you to remember, as I told you, I will go through this lecture through the main points that I want you to review, starting from the addition and the various properties related to addition. And it's not just only in matrices, if you remember. It's in matrices and also in vector spaces. It's one of the main conditions of a vector space is to have an addition closure. So let A, B, and C be any matrices of the same size, m by n, and alpha and beta constants. Then you will have this property, the associativity law, the identity for an addition, which is the 0, and also the existence of the additive inverse, which is negative A. Okay? All of these properties are really very important. Also, you know that there is, although in multiplication matrices are not commutative, but in addition they are commutative. So A plus B is equal to B plus A. The distributive law, either by a constant, and if you have two constants and multiplying them, and also once more, although we are reviewing the properties of addition and multiplication by scalar in matrices, it's exactly the same conditions that we already did go through in the previous lecture, if you remember, through vector spaces and what's related to it. Also, the existence of a multiplication identity, which is the real number 1. If you multiply negative A by negative alpha by A, I want you to put in your mind that I can multiply negative times A then by alpha, and these propositions are really very important. As I told you, on next Sunday, inshallah, your exam, I want you to review once more, I'm insisting, go through the propositions. You will have questions targeting this part, so you should study them very well. I think after that, we talk about the transposition. And all of you now, for the transposition issue, it's very, very simple. All I have to do is to replace the rows into columns and vice versa. It's very, very easy. The definition is A transpose of I and J is going to equal to A of J and I. So simply, instead of having an element with 1 and 2, it's going to be 2 and 1. 1, 3, it's going to be 3 and 1. This is how the process of transposition happens. You have this example, which is already in the slides. You have this matrix, which is m by n. Once you do your transposition, it's going to be an n by m. Okay, this matrix is 2, 5, 1, and 3. If we want to make a transposition, just to make you remember, all I have to do is to replace the first row to be the first column. So it's going to be a 2, 5, then 1 and 3 for the second column, as you can see. Also, this is for a row matrix. It's going to be a column matrix and so on. What's really important in this part is I want you to go through the propositions once more. So if I have A plus B transpose, it's going to equal to A transpose plus B transpose. If I have alpha times A transpose, so it's going to alpha, it will be a number, so it will remain the same, and you have the transposition. Of course, a transposition of a transposed matrix, you will regain the original shape of this matrix. Because it's like circulating the matrix 2 times, so it will regain its main shape. Also, I want you to remember in all times, that's really very important, it's the condition of symmetric matrices. How to know if there is a matrix is symmetric, or how to take the advantage. If I told you there is a matrix and it's symmetric, Mr. Hussein, that's A is equal to its A transpose. So they both equal to each other. And of course, in skew symmetric, you will find the transpose equal to negative of A. These two statements and two properties are really, very important. Although, also, all the details of these slides, you will find them in the main lectures. But this is just a sum up for these values, or for these propositions. Once more, transposition can be distributed on addition. A transpose of a transpose matrix is A. Also, we know that the symmetric matrices A transpose equal to A and A transpose equal to negative A. There is also something very important in symmetric matrices, that the principal diagonal elements are zeros. Don't forget this. But in the symmetric matrices, it's not a condition, it's not necessary. But in skew symmetric or any symmetric matrices, they are the same. Okay? You will have the principal diagonal elements equal to zeros. And this is the definition in front of you. Okay, in multiplication of matrices, you have a critical condition for multiplication. That's the columns of the first matrix should equal to the rows of the second matrix, as you know. And the result will be the rows times the columns of the second matrix. Are you with me? This is really very important. Okay, that's a symbolization of how you multiply the row by a column. You multiply the corresponding elements, and then you sum them up, and that's the short written expression for the multiplication of two matrices. If I have just these two matrices, which is 3 by 2, as you can see, and this one is 2 by 3, if I want to multiply them, so already the condition is valid. This is 3 by 2, and that's 2 by 3, so the columns of the first matrix equal to the rows of the second matrix, and of course the dimension of the resulting matrix will be 3 by 3, as it will equal to the rows of the first matrix with the number of columns of the second matrix. So it's going to be 3 times 3. Also, if I have ABC matrices, and these are the propositions of multiplication, which is very, very important. If A belongs to any m by n matrix, remark that if you multiply I from the right, it is In. If you multiply from the left, it's going to be In, and the result will be A. That's a generalization for the multiplication by an identity matrix. So if we regain the last matrix, if I'm multiplying an identity matrix from the left, it's going to be 3 by 3. If I'm multiplying from the right, it's going to be 2 by 2, and so on. This is for the multiplication by the identity matrix. If I have 3 matrices multiplied in each other, I can choose any 2 of them by the same order, because we know that multiplication matrices is not commutative. It's not like numbers. So I would go for having AB first and getting the result, then multiplying in C. It will give you the same if you multiply with the same order. You have to remark the same order. B and C first, and the result will be multiplied in A from the right. Because, as I told you more than once, multiplication in matrices is not commutative. I can distribute either from the left or from the right for a multiplication of a matrix plus 2 matrices gathered together, or the addition of 2 matrices. So it's going to be A times B plus A times C. If I'm multiplying from the right, you will do the same. It's going to be C times A and B times A, and so on. If I have a constant multiplied by the multiplication of 2 matrices, I can multiply this scalar by one of them, and then multiply the result in the other matrix with respect to the same order of multiplication in matrices. Are you with me? See? Okay, this is really, very important. This is a huge important property. This is a very important property, Mr. Omar, which is if I have A times B transpose, okay, it's really, very important that you will have to replace the order and the transposition. So AB transpose, it's going to equal to B transpose times A transpose. And it's exactly like inversion. So transposition in multiplication of matrices, it's exactly like the inverse in multiplication of matrices, which is a really, very important thing. This is important. Okay, you have A, if it's a square matrix and you have a multiplication, so given n belongs to n and the square matrix A defined in the nth power, so A to the power of n, it means you will multiply the A matrix in itself n times. Of course, I want you to remember the embodent matrices. Omar, do you remember what's the embodent matrices? The embodent matrices are those types of matrices. Once you multiply A in itself, it will equal to A. So A actually equal to A squared. So this concept of, or this special case of having A equal to A to the power of 2, this is a remarkable property for some certain class of matrices, which is called the idempotent matrices, where A squared is equal to an A. I believe I already gave you previously an example on this idempotent matrices, and it's an important one. Of course, A to the power of 0 is going to be the identity, which is the unit matrix. Notice the okay. Of course, if you multiply a matrix by itself, there will be no order in multiplication, because from the left it's going to be exactly like from the right. You are multiplying in the same matrix. Okay, this is also, which is really very important, as I told you, for this type of propositions, when you have a power to a matrix. So if I have A to the power of m times A to the power of m with the same matrix, it will be the addition of their powers. If you have A to the power of m and then multiplying by k, it's going to equal to A to the power of m by k. Note that AB to the power of n doesn't in general. You can generalize it. It's correct in some certain cases, but it is not necessarily true. Do you read me? Which is A times B to the power of n, it's not going to equal in general, but it may happen in some certain cases. Okay? But in general, AB to the power of n is not going to equal to A to the power of n times P to the power of n. They will be equal to each other if they commute. What's the meaning of commute? A times B is equal to B times A. So that's the only condition. Multiplication is not commutative. However, if you have AB is equal to BA, so if I give you this piece of information before you start, then it's going to be equal. B to the power of n is going to equal to A to the power of n, B to the power of n. Of course, A plus B to the power of 2 doesn't equal to A squared, B squared plus 2AB, because of the that matrices are not commutative. And remember, when we were studying vector spaces, we already did go through something like this. The various conditions are okay, but for the multiplication of A squared and the adding an element with a power of 2 to another element to a power of 2, it's gonna fail the addition closure, if you remember. We already have something like this in the previous lectures. So this is really very important remark. Of course, if I want to expand this, Ya Omar, I will multiply A times A, then A times B, then B times A, then B times B. This is why we don't add them together, because matrices is not common. The inverse of a matrix. The importance of the inverse of a matrix, it is the main key of solving a system of equations. Plenty of properties and applications depend on the knowledge of an inverse of a matrix. And it's really very important to gather the propositions about the inversion. Okay? This is important. Okay, once more. AB equal to BA is equal to IM. That's B is going to equal to A minus 1. So if I have a matrix and multiplied by A minus 1, the result will be the unit matrix. And each matrix, if it is invertible, the inverse will be unique. I want to prove this proof. The proof by itself is not that important. But I want to go through the steps with you. Omar, leave your cell. Note, if A belongs to a set of n by n matrices and they are invertible, and its inverse is A minus 1, and it is unique. So I wanna prove this identity, or this reality, that the inverse of a matrix, if it is invertible, is unique. Look how he did it, step by step. I'm not really into the proof by itself, but into the process. How he manipulated, how he multiplied, and something like this. So let's remark first that I have the condition, or I want to prove that A times B is equal to IN. And also I know that A times the inverse is equal to IN, either from the left or from the right, if you remark. We multiply A times A minus 1 and the A minus 1 times A. Look to this fact.
since AB equal to I, and this guy, A minus 1 times A equal to I can say that AB is equal to A times A minus 1. Since this guy is equal to I, and since that guy is equal to I, so they are equal to each other. Logic. Am I right? So once they are equal to each other, I want to remove A matrix. How to remove the A matrix? I will multiply both sides in A minus 1. So multiplying, you will have to choose from the left or from the right. I will choose from the left. Multiplying from the left, it will make A minus 1 times A times B. And then A minus 1 times A times A minus 1. So actually, A minus 1 times A, it will be a unit matrix, which will leave the B matrix as it is. And the multiplying A minus 1 times A also will kill these two matrices. They will fly with each other equal to identity. So all you have is I times B equal to I times A minus 1, which proves that B is equal to A minus 1. And that's a proof for uniqueness. I'm not caring much about the proof, but the procedure. How to remove the A matrix multiplying by A minus 1. How to make two sides equal to each other by looking if they equal to another value, and so on. So this step is very important, how they equate these two parts, how we put them, or to choose the two sides that I will work with, multiplying by A minus 1 from which side, and the results of multiplying by the inverse, simplifying, and knowing that A minus 1 times A is equal to Y. Okay, this is really very nice. This is the only reason that I give you this proof at the time being. What's the elementary matrices? Anyone? Do you remember what's an elementary matrix? Jumana, what's the elementary matrix? The elementary matrix is an identity matrix. Okay? What's the identity matrix? The unit matrix, which has one on the principal diagonal where the other elements is equal to 0. The identity matrix, I can manipulate it, replacing the rows in each place, or multiplying a row by a number, or multiplying the row by a number and adding it on another row. And that's a very important part, and it will have to be covered in your exam, Ya Omar. So mainly in your midterm, or in the other midterm for improvement or something like this, or the global exam, hopefully you are not going to need something like this, but remember the part of the elementary matrices is really very important. What I want you to put in mind that the elementary matrices are unit matrices, unit matrix, but you just replace the rows and so on. I have how many elementary matrices? I have 3 types of elementary matrices, Mr. Hussein. Okay, 3 types, which are replacing rows, multiplying row by a number, and adding it on another row. So if I'm talking about an elementary matrix 3 by 3, that's elementary matrix, let's say R1 into R3, which means I will have a unit matrix, but I will replace the first row instead of that third row. So it's gonna be a 0, 0, 1, 0, 1, and 0, 1, 0, 0. If you remark, I've replaced the first row in the place of the third row. That's an elementary matrix responsible about moving rows in a matrix. How it's gonna move rows in matrix if you multiply this matrix by any other matrix. So it's mainly multiplying the elementary matrix by another matrix. What's the result? It will remove or replace the rows. Okay, I have another one, which is E alpha R. Let's say alpha R2, which is responsible about multiplying the second row in alpha. So it's gonna be 0, alpha, and 0, 0, 0, and 1. And that's for the second elementary matrix. The third elementary matrix is multiplying certain row in a constant, in a scalar, and adding it on another row. So if, for example, I want to get E of R1 plus 2R2, it's gonna be really very simple. All I have to do is to multiply first the last row first,
the last row in 2, then adding the result on the first row. So it's going to come up to 1, 2, and 0, and the last row is 0, 0, and 1. This is the third elementary matrix. The part of the elementary matrices is essential in any exam, in the formulation of any exam, because it's a part of the exam, it's main part of our course. Okay, once more, this is I3, this is R1 into R3, which is called R1 R3. This is I3, this is multiplying second row by a 5, and this is the third one will be multiplying the row and adding. Just skip it for the time being. Of course, one of the very important remarks, and I've solved more than one problem like this with you, you will have to review it before the midterm. If I'm doing more than one elementary matrix, and I'm getting the inverse of these matrices, I want you to remember that doing the inverse of the elementary matrices, it means you will do how many processes? 2 of them. First, you will reorder them. And instead of having EB and so on, you will have to reorder them. So already they reordered. And each one of them, you will get its inverse. What's the inverse of this matrix? It's itself. The inverse of the matrix of removing or just replacing rows, it's going to be the same matrix. What's the inverse matrix for this one? Multiplying by 1 over alpha. I have multiplied even alpha, so I will multiply 1 over alpha. Yeah, Omar, what's the inverse of this matrix? It's multiplying by R1 minus 2 R2, which is gonna, cancel what you did already. This is really very important part, as I told you, from the elementary matrices. Remark the inverse. If I have B is equal to EB, blah, 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 blah. If I want to get A minus 1 or to get A in one side, I will multiply these matrices in the other side. خلي بالك Mr. Hussein, once you are multiplying, you will do how many processes? 2 of them. Replacing the order, and this is confusing, and getting the inverse of each one of them. And that's really, very important. Another remark, of course, the elementary matrix, it has the same rank as the identity matrix that you are using. Okay, what's a Gauss elimination process to play with the elementary matrices or the row operations? Do you still remember the row operations? Replacing rows, multiplying row by number, multiplying row by number and adding it on another row. The Gauss elimination process consists of working out your matrix in order to get to echelon form, which is an upper triangular matrix. And then go substitution from in the backward. So you start from the bottom of your matrix, getting each variable step by step and going up. But for the Gauss-Jordan elimination, we are going to use the row operation in order to reach a reduced echelon form. The reduced echelon form will lead to the solution directly. So I don't have to do row operations to get to echelon form and do substitutions. No. I will do the reduced echelon form and the result will be with you. That's the difference between Gauss elimination, Gauss-Jordan elimination. Of course, you have the pivots, and you know the pivots are the ones on the principal diagonal, okay, when you are trying to reach a reduced echelon form. Also, one of the most important definitions, and which is related to this part, is the rank of a matrix. Do you remember what's a rank of a matrix? The rank of a matrix, the number of non-zero rows in a matrix, once it reaches an echelon form already, I would prefer reduced echelon form. Okay? This is, you will get the rank of a matrix. Remark, any linear system has either no solution, a unique solution, an infinite number of solutions. So at least you will have to solve one of the problems from the sheet or from the previous lectures already recorded, and you have it on the YouTube, okay, of having this classification. Okay, Omar, are you with me? Do you know which part that I'm talking about? When you have a system of equations which have an additional constant. And he is asking you about the value of this constant, which will make this system have a unique solution, a no solution, an infinite number of solutions. This is really very important, the classification point. Okay? Also, a system of equation either linear or non-linear. Non-linear, we don't deal with non-linears. Non-linear, or we didn't go through non-linear, because the process of solving a non-linear system, what's the non-linear system? That you are solving a system of equations where the variables are multiplied in each other, or one of the variables, even at least one of the variables, having the power greater than 1. So I'm solving a system, for example, x squared plus y plus z equals some value. Did you remark? X squared, x to the power of 2, plus y plus z. The second equation, x plus y plus z. The third equation, xy plus z equal to a certain number. That's a non-linear system, of course. Why it's non-linear? Because you have two variables multiplied, or one of the variables with power greater than 1. We are dealing with linear systems. Okay, a system of equations, either linear or non-linear. We didn't study this. We are studying linear. And is said to be inconsistent, it has no solution, or consistent, it has at least one solution. Why, when it is consistent, it has at least one solution? Because consistent solution, you have two types. Either the unique solution or the infinite number of solutions. So, your system mainly is classified between inconsistent, no solution. Consistent, it will have two types of solutions. Either one solution or infinitely many number of solutions. And we already studied all of this previously. Note that if A is equal to 0, and that's a very good remark, if I'm solving a system which is AX equal B, and the A is equal to 0, this system will have a solution only if the B matrix is equal to 0. And this solution will be infinite number of solutions. Are you with me? Okay, that's a very nice remark. Okay, so note that if A is equal to a 0 matrix, then the linear system, which is 0 times x equal b, is consistent only if this B matrix is a 0 matrix also. And in this case, it will be infinite number of solutions. Are you with me? Because any combination of the x column will prove these equations. So it has an infinite number of solutions. That's a trivial system. Ax is equal b, a linear system of equations. This is very important. If the rank of A less than the rank of A and B, which is the augmented matrix. Juma, when you solve a system of equations, usually you will have your coefficient matrix and the augmented matrix. What's the augmented matrix? So if I'm solving a system of equations, let's say I'm solving Ax is equal to B. The first step is you are going to take your coefficient matrix and put it in here. Then you will have a dashed line and you will have the result matrix. These two matrices together, they form the augmented matrix. This guy. So if the rank of the coefficient matrix is less than the rank of the augmented matrix, you have no solution. This will happen only if you have zeros in the coefficient matrix and this element doesn't equal to 0. This is the condition. Okay? So, in this case, you will have no solution. Because the rank of the smaller matrix for sure will be less than the rank of the overall matrix. Are you with me, Mr. Hussein? So, this is really very important. Very important. Okay, if the ranks equal to each other, if the ranks are equal to each other, so the rank of the smaller matrix is equal to the rank of the augmented matrix. Now I will look to the number of variables. Now I will go for the number of variables. If the ranks are equal to each other and equal to the number of variables, you will have one only solution. Because you will get a reduced echelon form of a unit matrix. So it will lead to a unique solution. But if the systems are equal to each other, this is the case if they are equal to it, but less than the linear, less than the number of solutions, the number of variables, you will have infinite number of solutions. This is very, very important. So, if the ranks equal to each other, you will have a consistent system. If they equal to each other and they equal to the number of variables, a unique solution. If they equal to each other and then the number of variables, then you will have infinite number of solutions. This part is important. You will have to review it very well, at least try to solve one of the problems that we did go through previously. I believe in week number 6, I've reviewed most of the midterms, the previous midterms, and also did go through plenty of problems containing this part, so you will have to go through them. These are the various cases as I told you. Now I will go to determinants and the probabilities of determinants, and this is also a major part that will be represented or will be found in your midterm. Determinants, they are assigned the values to a matrix. The trick in determinants that they have a very close probabilities to matrices, but with minor differences. You have to remember the differences. So first of all, these are the rows, so you can symbolize the determinant by just putting just 2 lines. So that's a symbol of a determinant of a matrix A. That's a determinant of matrix A. That's a determinant of A. That's a determinant of rows. All of them means a determinant of a matrix. We call determinants to array valued functions. Okay, so it will equal to a certain value. I want you to remember the homogeneity in each row, which means a determinant of row number 1, row number 2, alpha, I can take a constant just only from one row. And this probability is completely different than matrices. If I have a matrix, I want to take 2 as a common, it will go from all the elements of the matrix. But if I have a determinant and I want to take a common, it will go out from just only one row or one column. Don't you ever forget this main point. And also it will be reflected in multiplication by scalar. Also, if you have 2 rows, 2 matrices, 2 determinants, and you need to add them together, the only thing that will be added, just only one row or one column. They have to have the same identical rows and in order to add them together. So simply,